better environment, hopefully also for the video. Okay, so what we did last time, that was admittedly a little bit abstract. So I can promise already we will now shift gears, at least for one lecture totally, and most of the time today speak about implementation. So that's where the CE students can show all their brilliance, and hopefully also the mathematics students. So, but before doing so, let me first come at a remark along these a little bit more functional analytic lines. Maybe I switch off here. The should be still okay for the video? Okay, good. So what we said is what we are doing by solving a variational equation in the abstract form. That means we have a space, a normed space capital V. We are looking for an element U from V such that AUV is some linear form BV for all, say, test functions from the same ansatz space. That is what finite elements is also. What the characteristics is, we have the same space for the solution and for the test functions. That is nothing but an operator equation, AU equals B, and as assumptions, of course, we need to have that the B is a linear form. I write this in this form with a star, and the A is bilinear. That's all what we need. But now we have had further assumptions in dealing with some principal problems like stability and convergence and so on. The one property was this V ellipticity, and the other one was the continuity of the bilinear form. And I said this condition, this boundedness condition, is equivalent for a bilinear form is equivalent to the continuity assumption. This is equivalent of saying A is equivalent at some pair UV or at the pair 0, 0. It's all equivalent as in the linear case. So let's have a look what this means. So first, remind how this A is defined. At the moment, the A is an operator from V in the algebraic dual. So what is the algebraic dual? Again, these are those functionals, those phi from going from the vector space to the reals, such that it's a linear functional. As in linear algebra, the algebraic dual. Okay, and the definition is U is mapped to AU, and this is then the argument here. And because of the bilinear, this is a linear form. And we know a little bit more about the A because the bilinear form is also linear in the other variable. We know that it's not just any mapping, that's a linear mapping. So A, I now avoid further symbols. I just say A is linear from V to V star. That is, so to speak, the algebraic situation just coming from the bilinear assumption. Now, in addition, we have this continuity assumption. What does that mean? The continuity assumption tells us now we have the assumption A is continuous. That is, we can estimate AUV for arbitrary arguments U and V in modulus by some constant which we have denoted by M times norm of U times norm of V. So what does that mean? First, what does this mean for AU? This is AU applied at some argument V. That's just what it says here. So that means, what does that mean? That means the linear mapping AU is not only linear, it's bounded. And a possible constant, boundedness constant, we can read from here. This is just this number here. m times norm of u. Because it's just this number says number times norm of v estimates the norm of this thing. So the first thing is we see a of u is not only in the algebraic dual, it's also in the topological dual, which is by definition those v which from the algebraic, those phi from the algebraic dual which are continuous. And as we are talking here about linear functions, continuous means bounded. That is what we have checked. We have checked the boundedness. We have checked the boundedness, and we have a norm. This space, in general, this space is a strict subspace from the algebraic dual. And we have the identity of those spaces if and only if we are in the finite dimensional case. In the finite dimensional case, all linear functions, all linear mappings are continuous, are bounded. Okay. So in addition, we have the induced norm, the operator norm, or then in the finite dimensional space, more specifically the matrix norm. We have the induced norm on the dual space, and we know in this norm, we know what the norm is, so to speak, the best possible constant in this estimate. We have seen this is a constant, so the best possible constant is less or equal than m times u norm. But what does this say again? This says that the mapping A now, not the image AU, that the mapping A from V to V star is continuous. Sorry, not from V to V star, now we are from V to V prime, is continuous. So that is what is behind this assumption, as an amendment to what we have discussed last time. So now we will change gears totally and speak about implementation. Okay. So we will first talk about, so this is a very classical point of view of finite element method implementation. Oops, why is this frozen? Should not be. Maybe it was not a good idea to go in this room. It's not frozen, but the stupid machine thinks it is frozen. So what do? We try switch it on and off. That is computer science. If your car does not work, you step out and then you step in again. Okay. What we have here, one. So we restrict ourselves now again to the model problem, but we will see in the process of working this out how this can be generalized. So first of all, we have a domain in R2 only. It's polygonally bounded. We use linear ansatz functions on triangles, and the underlying problem is this one. It's the Poisson equation with homogeneous Dirichlet boundary conditions. Later on, I will tell you how to include Dirichlet boundary conditions. This will be only operational. I will just tell you how to do it. And later on, we will understand why this is reasonable to do it like that. So there are three basic steps to do. One is the so-called preprocessor, then the assembly stage, and finally the solution of the emerging set of equations. Okay, still in the process of getting out. Okay, so what do we have to do? We have first to do some things before we are able to compute the entries of the set of equations. So the first thing is we have to define the domain and we have to define the triangulation. In our case, with or in general, in fact, it's sufficient to define the triangulation. By defining the triangulation, you also define the domain. So let's first do this. So we have first to specify the nodes of the triangulation. To do so, we need a list, or this we can do just in a simple array, which notes the coordinates, in our case the x and the y coordinates, and in other dimensions correspondingly modified, of the m variables what we have. Keep in mind that in the case of Dirichlet data, we include these boundary points. So we look at all boundary points, and by this we are also able to then define the domain out of this information, and as I said, we will later see how to include Dirichlet boundary conditions. Okay, so what we do here in this way, in the way we number these coordinates, in this way we number the nodes, we define a global numbering on the set of nodes. Okay, so we have these are the quantities we have. The m is the number of total variables, of nodes, and then we have to relate the. Looks a bit strange what this projector does, but anyway. Then we have to relate those nodes to the geometrical objects, in our case the triangles. That means first we have to know, of course, how many triangles, and then we have to know which triangles. And which triangles is encoded in a so-called element node table, element Knotentabelle, in which we give for each triangle, which also has a global numbering, the nodes which are involved in terms of their numbers in the global nodal table, Knotentabelle. So for example, if we define in this array the 10th row, that would describe the 10th triangle, and we say the 10th triangle is supposed to have the nodes for 11 and 7. Of course, this is not unique. It's also not important that it's reasonable to use, for example, counterclockwise ordering here. This facilitates some of the following computations. Okay, so of course this looks quite tedious to do so. And in fact, when I started off in doing so, this was in the, when was this? At least in the early 80s, in any case before you have been born. We worked on a geological problem, and what we really did, we did the triangulation by hand. This is not the situation nowadays. In principle, we only need a very, very coarse triangulation to define the domain. The domain is then defined just, of course, by the union of all the triangles. And so what we could do is we could say, okay, if I would like to have this domain here, and I would like to use triangles, I can define this domain by setting up this structure here. So I have 4 nodes, and I have 2 triangles. Of course, this is not a triangle. This is not a triangulation in which I can reasonably do computation. In this case, I would have no interior node whatsoever. Also, this is a very coarse triangulation with 1 interior node. It's also does not give a very precise approximation. So an easy way to do is, that is, so to speak, the most easiest way to do grid generation. So now the notion of grid generation comes up. We have a definition of the domain, and we want either to refine an existing triangulation or just to define a new triangulation. Let's only look at the point to refine an existing triangulation. And this can be done quite easily here in this case. So what we are doing here, we take every triangle and introduce as new nodal points the midpoints of the edges, and in this way we subdivide the triangles in 4 triangles which are all congruent to the large triangle. And we will later see, I've indicated this already a little bit last time, that the quality of the triangulation plays a role also for order of convergence estimates and for the behavior of the method. And this quality is measured in angles or in quantities related to angles, and that means by this procedure we preserve the quality of the triangulation. The disadvantage of this procedure is that you see it here. So what we could do, so in this way we could very easily define the Friedrich-Scalar triangulation. If we have some procedure which does this refinement, it's also called the red refinement for some reason. We just define our rectangle in this way. There's not so much to put in by hand. And then we do 1, 2, 3, 4 refinement steps, which in the end gives us a triangulation which is as fine as we would like to have. If you want to have something like the Friedrich-Scalar triangulation, this is quite okay. Okay, yes. Apparently this guy is not working here. It's frozen, but okay. So we have to restrict ourselves now to this projector. And if we want to have a uniform gridding on a general domain, that's also okay. You see here, this is a more general domain, and if you proceed with that, you get a uniform gridding in the sense that all the edges here have more or less the same length, and they will preserve, and all the edges in each of the refinement steps will also have more or less the same length, because the only thing what you're doing is halvening the edges. That means if you want to have, but the flexibility of the finite element method in particular allows that we, say, make our grid at critical points of at critical subregions of the solution more dense. You may imagine if you have a solution which is more or less flat in some parts and you don't need too many discretization points, but then there are subregions where it changes very rapidly, then I think it's intuitively clear that you should have a more refined discretization there. This we cannot produce in this way, and I will discuss how we can do this in a simple fashion. So we will only scratch a little bit at this problem of grid generation. So what could we do if we want to have a non-uniform refinement? Of course, we could say, yeah, okay. For example, we want to have this upper triangle more refined than the others. So we do a step where we only refine the upper triangle. What is the problem which I have produced then? If I only refine the upper triangle, then, yeah. I don't have a conformal triangulation anymore. So I get what is called a hanging node, a node which is in the middle, from the, so to speak, seen from the other side, is in the middle of an edge. And there are methods which allow for that, but we are not going to allow for that now. So we have to do something here, and that is then the so-called green refinement. That means what we could do, maybe I draw a picture, if we So maybe I can copy this somehow. So we have something like that. Some strange domain. And we have those 4 elements, and this we now refine. And now we have the problem with these 2 nodes here. And the most easiest way to handle with these 2 nodes to say, okay, now I have to make them to be vertices of triangles again. That means I have to subdivide this triangle now in 2 triangles and correspondingly this one. And this step is called then the green refinement step. You see the problem which comes up. What I do is I halven the angle without changing the maximal the length of the maximal length of an edge here. And this is, we will see this later on, more detail. This is bad for the quality of the triangulation. So we should not do this too often, this green refinement step. And that is the idea which underlies a simple algorithm which I'm now going to describe. And this goes as follows. So we have some coarse triangulation, and we have some places where we want to refine, and these we indicate the corresponding edges of the triangles as to be refined. These will be the so-called red edges, rote Kanten. Now we have some refinement criteria which tells us how small the h, the local h, should be there. And according to this refinement criteria, we just subdivide the edges. For example, here our refinement criteria tells us first subdivide in 2, then let the right-hand part be as it is, and take the left hand, subdivide it again, and then subdivide here. So we produce, in a finite number of steps, we produce new nodes. And then the next step is we look at each of the triangles and see how many additional nodes have been produced in addition to the edges which are already there. If there are 2 or more additional nodes, we subdivide this triangle in 4 congruent triangles, so we do a red refinement step. And we do this as long as only triangles are left which have 1 additional node. Or, of course, none. And then we take the triangles with 1 additional node and do a green refinement step. So we subdivide these remaining triangles in 2 triangles. And if we, in a later stage, or if we're not satisfied with this refinement, and we want to do further refinements, we first remove the green edges, not to produce too many green edges. So let's have a look how this might work. Okay, so this is our underlying uniform Friedrich-Scalar triangulation. For some reasons, we would like to have nodal points here. Okay, now we see this triangle has 2 additional nodal points, so we subdivide it. This also. And then by this procedure, now we loop over this step, and by the subdivision of this element, here a further node appears for this triangle, so we also have to subdivide this triangle. So we end up in this situation. So we only have now those 2 triangles which have 1 additional node. So here we then do, and here. So here, and here, and here, and here, and here, we have to do then a green refinement step. These are these bolder lines here. And doing the same thing again with another example. So, okay, so we have first to subdivide in 4 triangles this one, and this one, this one, and this one. Here we are not yet done, so we have to further subdivide this one here again. And now we are in a situation that only 1 additional node appears. And now we have to add the green edges. Okay, that would be a possibility, a simple refinement strategy to produce a triangulation. As fine as we would like to have it, and with a distribution of the nodal points and with a distribution of the local fineness h as we would like to have it. Okay, so now we have this triangulation, and now we can go up to the assembly stage. That means to set up the set of equations, the matrix and the right-hand side. Okay, to remind what we have to compute. We have to compute for the entry ij of the matrix, and at the moment I'm, so to speak, using the natural indexing of the matrix. Later on we will change this. We have to compute those integrals. And we did this already in a node-wise fashion. So we looked at the nodes which were involved here, the nodes I and j. For specific pairs of I and j, we try to compute these entries for a special case. In the general case, we will do it the other way around, as you will see in a second. So the first thing that is quite trivial, of course, we can subdivide this integral in the integrals over all triangles. So we are left with the problem in computing those small entries here. So if you look at these matrices A, I, J, M, so in principle these are again large matrices of the dimension capital M, capital M. But as you know already, and as we remind us in a second, they have only a very few places they have entries. So we will store these matrices I, J, M, which are called the element stiffness matrix in comparison to the stiffness matrix, Elementsteifigkeitsmatrix, then in a local way. So what does that mean? So first of all, if A1 to AM denotes the nodes, then we know the only situation where we can have an entry here in this situation if these two nodes belong to the element M. So we only have entries if here nodes come together which belong to this M. So computing this part, we only have at the nodes which belong to this element. And you see these ideas which can be transferred to other types of elements. For example, if we would have a rectangle here or a quadrilateral, that would be the same thing. What does that mean? This very, very large matrix here has only entries at most 9 positions, 3 times 3 positions. So because of that, we store then this matrix, so we compute these matrices going through the loop of the elements. That is the element-wise approach. And first of all, we locally store this matrix in storing it in a 3 by 3 matrix. And to do so, we need a mapping between the global numbering which we have in a local numbering. So we are dealing with one specific element in this loop over all elements. And this element has global numbers here for the nodes. These numbers we can see in the element node table. We give in addition, we define a local numbering, as you see here, and now we will work in this local numbering. So in the global numbering, we would have a big matrix which would have entries only at the positions Ri, Rj, and now we compute those 9 entries in putting in a 3 by 3 matrix with a local numbering 1, 2, 3. So this is what is indicated here. So we go from the global numbering to a local numbering, and this is referred here with the tilde. This has nothing changed compared to the value we have to compute. And now we have to compute this 2-dimensional integral. Okay, so what is the problem? The first thing, what can we do? We have already used the reference element k hat to deal with the interpolation problem. And that's the same what we do now. So we now try to transform this integral to an integral on the reference element, and then try to work out this integral either exactly or later on approximatively on this reference element. So two things have to be taken into account. The one thing is, of course, the general transformation formula for integrals in several dimensions, which you hopefully remind. So first of all, we have to specify the mapping, and the mapping we know already. The mapping is just this affine mapping, bx hat plus d, where the d is in this local numbering the nodal point a1, and the others are the connection vectors a1 to a2, a1 to a3. So we know the d and we know the b. So we get in, we will see this later on by this transformation, we will get a factor here, and the factor which we get is the modulus of the determinant of the Jacobian of this transformation here. Okay, because this is an affine mapping, the Jacobian is just the b, so we get in the determinant of b in modulus. That's easy to compute quantity. It's a constant quantity because we have a affine mapping. If we would have a more general mapping, this would be an additional variable part of the integrand, which possibly makes it will not allow us to compute the integral exactly. Here in our special cases, we are able to compute these integrals. The next thing is we have here derivatives. But we have derivatives in the x variable, but now we would like to have derivatives in the x hat variable. So we have to apply the chain rule and try to compute what is now the x hat derivative of this composed function which appears if we now refer to the reference element. So we start now on the reference element, go to the specific element we have in mind, and then the function u is the next part of the composition. Okay, and if I note here the x hat, I just mean the derivative. The derivative meant as a linear mapping. And the representative, this we should have in mind, and if we have in particular a functional as we have here, so we have a mapping which starts in several dimensions, in 2, and adds up in a scalar value. What is then the matrix representation of the corresponding derivative as a linear mapping? Each linear mapping has a matrix representative, and what is it here? Is it a row? Is it a vector? Is it a full? Is it a 2 by 2 matrix? Or just give me the dimensions. What is it? So what kind of thing is this here? You have two choices, row or column. Who is for row? Okay, who is for column? Okay, 1 to 1. In fact, it's a row because we are going from 2 dimensions to 1 dimension. And of course, a matrix who does this is a column, is one row with 2 entries. This we should have in mind. So now we just apply the chain rule, say we get here the x derivative, and then we get the x hat derivative of the f. That is the thing we want to relate to. So this thing we have computed already. This thing we have computed already. This is just the matrix B. And now, why I have asked these questions, now we are talking here about gradients. What are gradients? Rows or columns? What is a gradient? Yeah? A column. So the gradient is just the transpose of the derivative. And this we have to take into account. So we transpose now the whole relationship we got here, and now we write it in gradients instead of derivatives. So we get here the gradient, which we would like to have in the integral, or which we have in the integral, is now Now we have transposed, so the order reverses if we have to put the b to the other side, so we could get b to the minus t, so the transpose of the inverse of b, times the gradient now in the x hat variable. Okay, so now we can substitute. First step is what I said already, doing the transformation to the corresponding new domain, we get this modulus of the determinant in. So we get the modulus of determinant of b in. Now we get those formulas in here. This here is the Euclidean scalar product. And for this quantity here, we use a shorthand notation. This is this one. So if we have the situation, we start at the reference element, go first to the general element we are looking at, and then have some function on this general element. Here this is now the basis function, not a general function. We write this in a shorthand notation with this function and a hat on top of that. So this just means this composition for any function f. So here it's given again, now here's again denoted for the function phi, and you can do it for any function. So if you have a function defined on a reference space with a hat on it, that means first go to this means that there's a function involved which actually defined on a general element. First go to the general element and then apply this function. So this is a shorthand notation. Now we can look at these functions. What are they? They are functions defined on the reference elements. They are piecewise linear, and they have the property that they have, what is this Rj? It is 1 at the node Rj, and it's 0 at all the other nodes. So in local numbering, it is 1 at node j and 0 at all the other nodes. But we have already given those functions, we have already given a name. This has been the shape functions, die Formfunktionen. So these were the shape functions which appeared on the reference element in conjunction with the question, is the interpolation problem solvable? So these were the functions x, y, and 1 minus x minus y in our case. So we have here the shape functions involved, we have the derivatives of the shape functions involved. So this is global, this is something global. This only has to do with the reference element. And the geometry of the general element we are working on comes in via the b at this place, at this place, and at this place. So we put this together a little bit. Of course, we can now in the scalar product, we can bring this matrix to the other side in the scalar product as its transpose, so as b to the minus 1, so b to the minus 1, b to the minus t. This again is b, is again, so this is this quantity, and this quantity again is b transpose b to the inverse, if you work this out. So we have here a matrix C. It's just this matrix here. We have here the gradients of the shape functions, and here we have determinant. Okay, now we see how to compute these things. The matrix we have as these connection vectors of the nodal points. So we have the entries of this matrix. These are just the scalar products. B1, B1 in the 1, 1 entry, B1, B2 in the 1, 2 entry, and the same thing in the 2, 1 entry, and so on. Now we have to, so this is this matrix here. What you would like to have is the inverse of this matrix. And this is something which we luckily can do to compute the inverse of a 2 by 2 matrix. What is this? What we have to do? We exchange the diagonal values. We give the off-diagonal values a minus, and we subdivide by the determinant of the matrix. So what is the determinant? This is the matrix. What is the determinant of this matrix? This is by the determinant multiplication theorem. This is the determinant of B transpose, or which is the same as the determinant of B times the determinant of B. So I have to subdivide by a determinant of B square. Okay, so let's see how what would be different if we would have a more general situation. We would not have the Laplacian, but we would have a general diffusive operator, say, where the diffusion coefficient is not 1, but it's a variable function or even a variable matrix. That would mean we have to compute integrals of this type. All what we did, we can do. The only thing is that now in this integral, say at this level, we still have this is now a notation overloading, but I hope you can bear this. I use now k both for the element and for the coefficient matrix. We would have an additional k evaluated at x hat here. All the other things are the same. So in the situation where there is no k, or there's only a constant k, we now can compute this matrix explicitly. So we have this we can compute this integral explicitly. We have the matrix C, we have this factor here. So okay, the determinant of a 2 by 2 matrix is also not so hard to compute. And by the way, what does the determinant represent geometrically for the triangle? What is it? What has the determinant of B to do with the triangle? This is high school 7th grade, something like that. What has the determinant? You have 3 points. You have the 2 connection vectors. The determinant of the 2 connection vectors. What has it to do with the triangle? What kind of geometric quantity is the determinant? We are looking at determinants. Yeah? No. In the end, it is something like that. But compared to what? Compared to a reference element. Actually, it is just the double. It is the area of the parallelogram spanned by these 2 connection vectors. So it's the double of the area of the triangle. And of course, if you compare a general triangle with our reference triangle, which has obviously the area 1/2, then it is the factor which relates these 2 quantities. Okay, so we work this now out. And we can write it, we just multiply this out, matrix times vector times vector, here in the scalar product, of course, and then we get these 3 contributions. We get the 1,1 derivatives, we get the 2,2 derivatives, and we get the mixed derivatives. And here are the factors which are in front of that, and all these quantities can be directly computed from the geometrical information of the nodal coordinates here. So the only question is, what about the you see it here. The geometric information is now in the gamma 1 to gamma 2 to gamma 3. And all the other things, they only refer to the reference element and the used ansatz space. So this is the same for each of the elements, as long as we take the same ansatz space everywhere in the domain, what we do up till now. So these are quantities which in our case can be computed, and they can be computed one and forever, those numbers. You don't have to compute them again and again going through the elements, they're always the same. Now how to compute those numbers? So these are then matrices, S1, S2, S3, which I just refer to the 1-1 derivatives of all the combinations, local combinations of the three shape functions, and correspondingly here for the mixed derivatives and here for the second derivative. Okay, these are not going in detail. This is clear that we can compute these integrals exactly. The gradients are constant, so we just have here specific constants in which we have to multiply with the surface, with the area 1/2 of the reference element, and that is what comes out. This is the table which comes out. You should check at least a few of these entries. And in the case, in the case, if we would have looked at this case, of course we could not do like that. Then we would have a variable part in the integral, and then we would have to use quadrature rules in the same way as we did it already to relate the finite element method to the finite difference method. That is, we substitute then the integral, the local integral transformed to the reference element by a quadrature rule by a linear combination of values. And what functions appear in these values? Yeah, the integrand. So that means those functions here appear. Okay, these are constant at the moment. So these are just the numbers I just indicated. But it also says, okay, if we have higher order elements, which we'll have later on, not using linear approaches, but maybe quadratic or cubic or whatsoever, then it might be possible still to compute these integrals, but maybe it's too tedious, and we maybe still would like to use a quadrature formula. Then we have to evaluate those derivatives at the quadrature points. And correspondingly, of course, now we have to evaluate the coefficient at the quadrature point, and at the quadrature points, and then do the linear combination, which is then the quadrature rule. And you see this evaluation at the quadrature points is again, at least for the shape function, something which can be done one and forever. Okay, but we stick now to our case, and what do we still have to do? We have to compute the right-hand side. The right-hand side is a little bit simpler in the sense that no derivatives appear. So we don't have to do any transformation, but the procedure is exactly the same. So what is the right-hand side? The ith component of the right-hand side is the integral of the right-hand side at the basis functions, and we saw already that we will run here in the problem that we can evaluate this exactly, so we do the same procedure till what we did and what we also did in this example. We split the integral up in the sum of the integrals over the elements. So this is a part in this big loop going over all elements. Then we do the transformation to the reference element. So the determinant, the modulus of the determinant comes in, and here we just have the basis functions, no derivative, so we just have the shape function, and so we don't have to do further transformations here. And here you see, in general, we will not be able to evaluate this integral. Maybe if the f hat is some polynomial, then of course we can do that, or some other special function. So here we will then use a quadrature rule, and here it's written down again what I said already. So we have an integral of this type on the reference element with an integrand g. And we substitute this by some quadrature rule, which has capital R quadrature points and quadrature weights. So we have to evaluate the g at those quadrature points and do this linear combination here. And if we do the trapezoidal rule, what we did already, that means we have 3 quadrature points which coincide with the nodes. So this would be the 3 nodes of the reference elements. And in the case of the trapezoidal rule, here we get 1/6 as the weight. It's the equidistribution of the 1. 1 divided by 3 is 1/3. And then we have to multiply with the area of the reference element with 1/2. So that would mean, doing so, we would have to have a term like that here to evaluate a term like that, and those are again quantities which can be computed only once. Okay. So now what we did now, that only happened for one element locally in the local numbering 1, 2, 3. Now we have to bring it back, but to bring it back, for that we just have to look at our element node table. We know at which element we are working, and we know which global nodal numbers correspond to the 3 local numbers. So we just, taking this into account, we just add these 3 by 3 entries and the 3 entries on the right-hand side, which we have computed, at the corresponding right places to the big stiffness matrix, which of course is not written down here. These vectors have to be initialized with 0 on this matrix. Okay, if we would do so, we would really say, okay, we store our matrix in a 2-dimensional fashion, and now we compute it as a 2-dimensional array, and correspondingly the vector. There's nothing bad about that, but now we come to the problem of later on we come to the problem of solving, and here I said already several times that we have to take into account the sparse structure, at least the banded structure, which we have seen already. And to do so, we have to change the numbering again. So in principle, everything what I now indicated is not to be done in this original numbering, but in a transformed numbering, which, for example, is adopted to a band structure or to a more elaborate sparse structure. This we will see in a second. So let me first indicate how to bring in Dirichlet boundary conditions. What we did up till now, we just ignored that we have Dirichlet boundary conditions at the boundary nodes, or at some boundary nodes. We just treated them as all the others. So what we do now, so it's also not of importance. So for the finite difference methods, to have a more nice notation, we said, okay, the Dirichlet nodes should be numbered as the last ones. That's also, it's not necessary here. We only have to know whether a node is a Dirichlet node or not. That's all what we need to know. So they can be somewhere in this global list. So we know, okay, what is the modification we are doing? We are going through our matrix on our right-hand side, that is through the rows, and look for the rows which belong to Dirichlet data. And then here we do the following. This row, what we have here, we just kick out. We substitute this row, so to speak, by the trivial equation which comes in from the Dirichlet requirement. So we substitute the whole row by the row U at the corresponding node should be G evaluated at the corresponding nodal point. That means we substitute it by a 1 at the diagonal value, zeros everywhere else, and the right-hand side correspondingly with a proper G value. So, if doing so, we have destroyed something in the matrix, at least if this property is there. In our special case, the matrix was symmetric, and if this matrix is symmetric, and of course, it's advisable to preserve the symmetry of the matrix, because this has a lot of advantages in solving the system. So how can we do that? We not only have then to change the corresponding row, we also have to change the corresponding column, which is now again identical with the procedure we did for the finite difference method. In the finite difference method, we basically did the same. We have not included this trivial line, this trivial row to the system, but what we did is we took the values, the known values, multiplied with the corresponding coefficients of the matrix, put it to the right-hand side, and that means we change correspondingly the right-hand side. This is indicated here. And we have changed the corresponding column to zeros then. we have eliminated the whole degree of freedom. But if we would have kept the degree of freedom in the way I indicated here, it would just have mean it would appear with a 0 in front of that. Okay, and this is also what we do, and in this way we preserve the symmetric structure. Is there one? Of course, it's not clear what this has to do with up till now, what this has to do with our finite element approach, and whether this is a proper way to bring in inhomogeneous Dirichlet data, so homogeneous Dirichlet data in the finite element sense. Homogeneous, maybe we can say it's quite okay. So let's first look at the homogeneous case. In the homogeneous case is what we do is we just, so to speak, kick out the basis functions which correspond to the Dirichlet nodes in this procedure. That is, and this more advanced thing really to take care of the heterogeneity G, then we have to see how this really fits with the finite element approach. Okay, now let's look how we solve those. Now we have finished, we have our system of equations, now we have to solve it. And here the question of the data structure also in particular comes up. There are two classes, you know this, I think, two classes of methods. There are the direct methods, which at least in an exact arithmetic lead to the solution after finite number of steps. Of course, this finite number of steps could be also pretty large if our system is pretty large, so it's not always an advantage to have a direct method. And there are iterative methods which compute a sequence of vectors which hopefully converge in a certain rate of convergence to the solution. So in a iterative methods, even in exact arithmetic, we never have an exact solution, but we have hopefully a good approximation, and we can control the precision which we have. We will start here with a discussion of the direct methods, which you should know either from introductory course to numerics or to numerics for engineers or something like that. I will repeat a little bit what we need. So we forget for a moment about the special things for our matrix. Just look at matrix A, which has a dimension m. And we look at a corresponding set of equations AXI equals Q, having in mind that our matrix A is sparsely populated. Of course, why are direct methods why are iterative methods so popular for this type of problems? The procedure matrix times vector is very easy to do. And this is so to speak, the algorithmic kernel which each direct method has. And assuming that the derived matrices which appear there in this method, derived from the matrix A, has more or less the same sparsity pattern as the original matrix. So this operation matrix times vector is easy to do, really only to look at the non-zero entries. I'll come back to this point in a second. But let's first start with the direct methods. And here we know that the direct method, that the Gaussian elimination, so the basic form is Gaussian elimination with row pivoting. And that means, and that is a procedure which always works for a non-singular matrix. And that means that equivalently, this means, I think you know that there is a permutation matrix B which reflects the row interchanges in the pivoting process, such that P times A is subdivided in a lower triangular matrix and an upper triangular matrix, L and U, or in the German notation L und R, links und rechts. Okay, typically the lower triangular matrix is normed in the sense that the diagonal elements are all 1. There's a certain degree of freedom in writing down such a product, from a lower and an upper triangular matrix, which basically means one can shift diagonal elements from left to right. And here is the uniqueness is here achieved by saying we have here ones on the diagonal. The upper triangular matrix is just the matrix you get by the Gaussian elimination process. And I hope you have seen that the lower triangular matrix is nothing but the so-called multipliers, the factors which appear in the Gaussian up to the sign in the Gaussian elimination process. So that means they can be in a dense version of the Gaussian elimination process. They can be stored in the positions which become oblivious. Here the zeros, which are not necessary anymore, so those else can be stored at those positions if one starts with a 2x2, with a two-dimensional array for the matrix and does this Gaussian elimination process. So that would be the classical point of view and classical implementation of that. So now the first question is, and maybe you have dealt with that also, in which cases pivoting is necessary? In which cases these permutation matrix really appears? And the answer is the following characterization, which is sort of a theoretical characterization, but I will go through the proof because it will help us then later on. The answer is we can choose the permutation matrix as the identity. That means no pivoting is necessary. That means we then call a matrix LU decomposable, LU zerlegbar, LR zerlegbar in this case, if and only if all principal submatrices, Hauptuntermatrizen, all principal submatrices are non-singular. What is a principal submatrix? It's a k by k matrix which just takes the first k columns and the first k rows. And we have discussed some time ago the question when is a matrix positive definite? And we spoke in particular about 2x2 matrices. And I think one answer which was offered to me, if the determinant is positive, this is not enough. Let's look at this criterion for the 2x2 situation. That means the determinant has to be non-zero, and the entry at the position 1, 1 has to be non-zero. That is the first, the 1x1 submatrix. And if we see if we now, in addition, and on the other hand side, a characterization of positive definiteness is not only that the determinants of those submatrices, the so-called principal minors, Hauptminoren, the principal minors of the matrix has to be non-zero. In the positive definite case, they are positive. That is one characterization of positive definiteness. So to cut a long story short, for a positive definite matrix, this condition is satisfied. So a positive definite matrix always can dealt with in the Gaussian elimination process without doing pivoting. And up till now, as long as we deal only with diffusion, also general diffusion, we always will end up with positive definite matrices. So let's have a look at the proof to draw some conclusions from the proof later on. So we will show this by induction, only one direction, I think, namely, but you will see that we can reverse those steps. This is really a characterization. So we show that in the case that the determinant does not vanish, so that they are non-singular, then we can do this decomposition. So in the first case, of course, in the k equals 1 case, we can do this decomposition here, obviously. Now, in the conclusion of the induction step, let us assume that for the index k we have such a decomposition, and let's see whether we find a decomposition 1 dimension higher for k plus 1. So we write the k plus 1 matrix in this block partitioning. So we have the matrix k. We have here a vector that is a column B, and we have a row C transpose. So if I use B and C, I always mean vectors, tuples, columns, and therefore I have to use the transpose here. And the D is just a number. So these are given quantities. And what do I would like to have? I would like to have an L, k plus 1, and a U, k plus 1. And the ansatz I'm going to do is I say, okay, I try to take those parts which I have already one dimension lower, the UK and the LK. Here I have to add a 1 because of the normed character of the lower triangular matrix. So I have an unknown vector L, and I have an unknown vector U, and an unknown number S. So can I find those three quantities such that this equation holds here? And if I multiply this out in terms of block multiplication, if I multiply this out, I come to these three relations. That means I have to I get my U by solving a set of linear equations, which I can do because the LK is a non-singular matrix in any case, because it has ones on the diagonal. I get dl by solving this lower triangular matrix. This also tells me how to, that it's easy to compute because this is only forward substitution then. And also the matrix UK is non-singular. Why is this? Because the product, because we said AK is non-singular. And AK non-singular means if I have a product LK, LK UK, then both of these factors have to be non-singular. Just look at the determinant of it. Okay, so if we have these two vectors, we just have to compute the scalar product of them, and this gives us a formula for the missing number S. So now what we have seen here, if the matrix is non-singular, then such a decomposition in the lower and upper triangular matrix exists if and only if all those submatrices are non-singular. This we have basically proven now. All the steps can be reversed. It's really an equivalency relation. So now we want to draw some advantage of this. Namely, we want to take into account that A has something like a banded, at least something like a banded structure. What does this mean for the decomposition? That means if A has, going back here, you've seen the B is, so to speak, a generic column, and the C is sort of something like a generic row of this matrix, because we come, depending on the K, we will see, so to speak, all the rows and columns at these places here. Assume that the B is of this structure here. We have first a first part in this vector of zeros and then something. And that would be the case if we would have a banded structure. What does that mean here for the computation of the U? I said we get the U by solving this set of equations. This is a lower triangular matrix. We do this. So what is the picture? We have here our L with the ones on the diagonal, but this doesn't matter too much. We compute here the U, the next vector of the decomposition matrix. And here we have a right-hand side where we have said first there are zeros and then there's something. We do this by forward substitution. We start with this, compute the first entry, then we compute the second, and so on. As long as we have zeros here, the corresponding part of the solution also has to be 0. Because up to here, this is again a non-singular set of equations, and for the right-hand side 0, of course, it has 0, or you just see it by looking at the formulas. Dividing the 0 by 1 gives us 0, 0 minus 0 times 1 gives 0, times something gives 0, divided by 1 gives 0, and so on. Okay, that is, we preserve this structure. And the same applies, because it's exactly the same thing, the same applies then for the row C. If the row C has such a structure that first there's a sequence of zeros, then there's something, then the sequence of zeros will be preserved in the lower part. So this refers to the upper part, and this refers to the lower part. Okay, so let's look at a matrix of this structure. And we see that those zeros which we have here, they will be preserved. Here we would look at this column, and the first 0 would be preserved. This 0 we don't know, but this is already in the lower triangle. It does not count. We are only computing an upper triangular matrix. But for example, look at this. Now look at the rows. We would preserve these two. We would preserve this, but we would possibly not preserve this one, because here some non-zero. So star refers to something, in particular to a non-zero entry. So we cannot say in general something about this value. So that means we start with a certain sparsity pattern. We can assure that some of the zeros are preserved, but some are not. Those which are not preserved are the so-called fill-in the matrix. And of course, we would like to have a matrix structure and a data structure such that the fill-in is as low as possible to reduce the amount of computations. Of course, we don't want to do the Gaussian elimination in a naive form, in a two-dimensional form, with all its m to the 3 complexity, where most of the time we are only multiplying zeros with something. That would destroy the advantage of the sparsity pattern, of the sparsely populated matrix. That would be as if we would have a fully populated matrix. Okay. So we will, in a second, we'll define this, this structure here in general, what this is. That is called the hull, the Hülle, or the envelope of the matrix, and we will then denote the amount of entries here in the hull. We will denote the profile of the matrix. But before doing so, let me first indicate a variant of the Gaussian elimination. I think you also know the Cholesky decomposition for positive definite matrices, and would hope that you also have recognized that it's only a symmetrized version of the Gaussian elimination. Let's have first a look that this is the case. So assume that we have a matrix which is LU decomposable. Then what we could do is we could write, okay, we assume here that is not noted here, that's possibly one more up, or it's omitted here. Here the assumption is that the matrix is symmetric here. That is here omitted. Okay, if the matrix is not symmetric, then the U can be decomposed in a matrix D, and in some matrix, let's call it L tilde transpose, which is norm. So we just take the diagonal elements of this upper triangular matrix, write it as a diagonal matrix, and multiply then, and then we in the second factor we can put the diagonal elements to 1. That's all. Now in the symmetric case we get this structure here. Why is this? And this is then the argument for that. Okay, here it's coming. So the first step is to do this here, to take the diagonal elements out and have here an upper triangular matrix which is also normed, which also has 1s on the diagonal. Now assuming that the matrix is symmetric, that is written here, the first thing what one should know is such a decomposition is now unique. I said the only possibility in changing such an LU decomposition is to shift the diagonal elements somewhere. And here I decided to shift the diagonal elements all in the middle, so to speak. So such a decomposition is unique. That's easy to prove. If I now do the transpose, I get now, what do I get? I get U tilde transpose, D transpose, it's again T, L transpose. So L transpose must be U tilde and vice versa. So I get such a symmetric decomposition in this way. So that is the situation for a symmetric situation where I have a LU decomposition. If in addition I now also have that the matrix is not only symmetric but also positive definite, those D values have to be positive. Because what I have here is just saying the matrix A is a congruent transformation of the diagonal matrix D. So if A is positive definite, D must be positive definite. But positive definiteness for a matrix is equivalent of having positive entries. So having positive entries means we can take square roots of this. Okay, we could also do this if it's greater or equal to 0, so also in a positive semi-definite case. And in this way we can subdivide, so to speak, the diagonal part in equal halves to the lower and the upper triangular matrix. So we write the diagonal matrix as its square root times its square root. Square root defined for diagonal matrices is quite obvious how to define. It's just defined by the square root of the diagonal elements. And on the basis of this we can also do something like the square root of a positive definite matrix, but that we don't need here. And now if we, so to speak, take L square root of T to one matrix, and then we get the transpose of this matrix. This is now this L tilde. This is now not normed anymore, but has positive entries on the diagonal. We get the Cholesky decomposition. The important thing to see is that the Cholesky decomposition is nothing but the Gauss decomposition with a certain scaling via those diagonal elements. And that means all the things we have said about the sparsity and the sparsity pattern in the Gaussian elimination also applies to the Cholesky decomposition. It's even easier there because we have only to store and to deal with 1/2 or with one of the triangular matrices there. Okay, so what we have seen already at the picture, we want like to define now in general notation. And to facilitate the situation, I'm not assuming that the matrix is symmetric, but I assume that the sparsity pattern is symmetric. So I assume that if Aij is non-equal to 0, then Abi is non-equal to 0. And if it's not the case, of course, I can define such a sparsity pattern which maybe is a little bit larger than the one I have and deal with this more simplified situation. But one could also deal with a general situation. So what are the quantities we are defining? The first thing is this FIA. So we go through the fixed row I, and we denote which is the first index where a non-zero element appears. And then we take the difference to the index of the diagonal, and this difference we call the left-sided row bandwidth, Zeilenbandbreite. Let's go to our example. So here we would have a 1, here we would have a 2, a 1, a 3, and so on. Okay. If you want to distinguish, if you don't want to assume this with a symmetric sparsity pattern, you have now to do exactly the same thing for the columns. And you will get different numbers. As we have assumed this symmetry, we could do it also for the columns, but we will get the same numbers. And taking this into account, we defined the bandwidth of the matrix in taking the maximum of those. So in this sense, the column bandwidth, the row bandwidth equals to the column bandwidth in our case, and we take the maximum of all those numbers which appear. This is then the bandwidth of the matrix. And the band are all those positions which are in here, ij and ji, which fulfill this, plus the diagonal. So we don't care what the diagonal, the diagonal always is added. This is always we have to take into account if we then do counting of elements. So, okay. So what do we see here? What is the bandwidth, the corresponding row bandwidth? So here we have 1 minus 1, so the row bandwidth is 0. So for a diagonal matrix, the row bandwidth in each position, and the column bandwidth also, of course, is 0. The diagonal is not counted. And correspondingly, a tridiagonal matrix, which you also know, has then the bandwidth, in this sense, the bandwidth 1. Okay, so here we get a 0. Here we get a 0. Here we have, so here we get also a 0. Here we have 3 minus 1, get a 2, and so on. And then we have to take the maximum overall, and taking the maximum overall, saying that we go going over all those diagonals and go to this diagonal, which has at least one entry. So in terms of the bandwidth, this matrix is quite disappointing. The only thing which is excluded here from the band is this and this entry here. So we have the bandwidth, we have the band, but we have also seen this is one structure we can work on. That's the most simple structure we can work on. But we have seen in terms of this fill-in, we can do it better. It's sufficient to work on the so-called hull, I think this word does not exist in English. I don't think so. In English, it's the hull, in any case. So what is this? These are those entries between this FIA and the diagonal entry for the row and for the corresponding column. And now if we count, so this the hull is here, this thing here, in between those lines. So this is a little bit smaller than the band. It's always smaller than the band, or at least not bigger. Okay, and then the last notion is the profile. The profile is just the number of entries in the hull. So we have to count those which are in the lower triangle, then the corresponding part in the upper triangle, then we get the factor 2, and this is the amount of elements on the diagonal. Okay, now what we saw already, we can put together in the following theorem. If a matrix A has a symmetric sparsity pattern, then the Cholesky, if it is applicable, that is, if we have a positive definite matrix, then Cholesky method and also the Gaussian elimination method without pivoting preserves the hull. In particular, it preserves the band, preserves the profile, preserves the bandwidth, if we look at the numbers. Okay. So the fill-in I discussed already. Now let's see what this means for our specific matrix. In our specific example, our matrix looks like that. And that means, we've discussed this several times, that we have entries only possibly in the situation if we have here neighboring nodes here. that means that we should take, we discussed this already a little bit already with the finite difference method, we have to take an intelligent numbering of our nodes. So different numberings may lead to different sparsity patterns, and therefore to different effort in solving the set of equations. So in our case, we can just say the definition, or this is a maybe we make then the sparsity pattern a little bit larger, because that's only a necessary condition here, but we can say for the FIA, we could say in this case we just look at the index where the neighboring nodes is. That is, we want to have that neighboring nodes do appear as late as possible looking at a specific row. Of course, this is not possible for all the nodes. This gives conflicts, and we have to see how we will deal with that. Here are some examples for matrices where we can do this without pivoting. That's not true for all non-singular matrices. But we saw already we could do it in any case for symmetric positive matrices. But the nice thing is it also holds true for M matrices. We have seen that the M matrices appeared in our special finite difference discretization. So in this sense, the M matrix is a generalization of the notion of positive definiteness to non-symmetric matrices. And later on, so in the finite difference case, so to speak, in the Friedrich-Scalar triangulation case, and the Laplacian, we have seen that the M matrix property appears in our specific matrix with the 4s and the -1s and so on. And later on we will derive properties for the triangulation. That's a question how the elements look like, so to speak, which preserve the M matrix property. It is a very desirable property also in the finite element setting, because we have seen maximum principle, no overshoots in the discrete solution, and so on. So I think this we can still do. Now, what are simple data structures? Maybe you have seen this already. Let's start with a symmetric band. So we have here the diagonal. We have then the super and subdiagonals. And here M is the bandwidth here. So we have the matrix, we have the diagonal, we have, so to speak, M band elements, M band vectors, and correspondingly also in the other half if the matrix is non-symmetric. So let's first start with a symmetric matrix. We only have to deal, so we deal with Cholesky, we only deal with one half of the matrix. And what we do is we just store this matrix in a compact fashion, trying to avoid most of the zeros which we would have here by storing it the way that we make vectors out of the diagonals. I think I would expect you have seen this already. So what does that mean? We keep the row index I, but the column index k is transformed to k minus I plus m plus 1, m being the bandwidth. And that is, we are going down from capital M times capital M storage requirements to capital M to small m plus 1. And of course, the idea is we have a large matrix, M is 10,000, and M is small. And we have seen in the example of our finite difference method, M is basically, small m is basically something like square root of capital M. So we will save something here. And that would mean now in this new numbering, the matrix is stored like that. Here's the diagonal. Here is the subdiagonal, so we store the lower half, and this goes down. There are still some elements which we don't use in the structures. There are some zeros put in, but it doesn't matter what you do with that. And the only thing is you have to now transform all the operations, all the index operations in this new indexing when you want to deal with. If you would like to do, you have a non-symmetric case, you can do the same thing. You not only have the lower half, but you have correspondingly also then the upper half. Okay, now if you want to work at the hull, not at the band, then a more maybe linear structure, a linked list structure, maybe is of advantage. And I've written it down here in a way which you could even do in Fortran, but of course it's more advisable to do it in other environments. So what do we need? In a hull, we only write down only the elements in the hull, in one linear list. But having one linear list, we have at least to be able to find where one row starts. So we need a pointer which points to the beginning of each row. So we know the row 1 starts at position 1, the row 2 starts at position 2, row 3 at 5, and so on. And this is a little bit more complex now to transfer this data structure in the assembly process, but it's principally the same thing. But we will, at the moment, I think we will basically work with banded structures. This is something which is more historical, which I skip. Okay, so the next question is, what is a good numbering? So what we would like to do is we want to reduce the bandwidth, we want to reduce the hull, the profile, and so we have to maybe it's another numbering of our nodes will give us better results. And this we will then discuss next week. Okay, let's stop here.